the range of interesting talks. Societal networks is being broadly defined, maybe with focal points in energy and transportation and communication to a lesser extent, but all over, it's really a question of a special time in the evolution of our science that brings together models and data and algorithms in interesting ways with all kinds of real-world impact. And one extra note that Peter omitted, that Pravin Varaya, and in an early stage of the discussion, he couldn't be here, Frank Kelly, were also part of the organizing committee for the workshop, so I want to extend my thanks to them. On with the show. So our first speaker is Bert Zwart, and as you can see, he's going to talk about a stochastic resource sharing network for electric vehicle charging.
Thank you, David. Thank you all for the organizers for the invitation, and it's an honor actually to be the first speaker of this great workshop. I was really looking forward to this a long time, and I did everything I could to be here. So I'm going to talk to you today about a topic. This is kind of, for me, like a breaking point between the past and the future. My background is applied probability in queues, and since a couple of years I got really interested in power systems, working on the reliability aspects for a bit, and then I came across electric vehicles, and so I'm just curious to see what you think. So this joint work with Angelos Avaklouris, who is a PhD student co-advised by Maria Vlasiou and me at the University of Eindhoven, where I'm 1 day per week. So motivation, you probably all know that the electric vehicles are on the rise and will continue to rise, and due to all sorts of drivers, especially the cost of battery getting cheaper, but of course all kinds of policy developments in policy and so on. And like you can expect it's going to stay, and there is a lot of effort going on trying to understand the impact and what we have to do to make this transitioning happening. And so there are, like at the moment, all kinds of different ways of charging your vehicle. If you charge it at home, typically you go sleep, and you don't really care from minute to minute on how fast your car is being charged. As long as you wake up, you want to be able to drive to work. It's similar to a fridge, right? If you open a fridge, I think Sean Mine once said that you open a fridge, you don't want to smell anything, and the light should work. And it's kind of like, in terms of communication, that works similar to best effort traffic. That if you want to download data, as opposed to voice, where you really want to have a good quality. To a lesser extent, if you go shop, this is an exhibition of the Dutch parking skills in Amsterdam. Then you want to have like maybe a slightly faster rate of charging. Then on the bottom left, we see a Dutch company called Fastnet. They're opening all kinds of fast charging stations next to Dutch highways. And there you can really charge your car in maybe 10 minutes. And Tesla has superchargers that can make your car charge in 5 minutes. And I guess this is all going to be able to go faster and faster. Last but not least, that it's also possible sometimes to swap batteries. I'm not going to talk about that today, but it's also an interesting way of thinking about how to deal with it. I guess in the future, I don't know if somebody's going to talk about that, you could even imagine that everybody's just sharing all kinds of cars, and you just, like as we did with horses, you just, instead of switching horses, you just switch cars. Maybe that will happen in the future, but like, I don't think, like for example, with my kids making so much dirt in the, I don't think it's going to happen that anybody wants to share my car, but okay. So I'm going to mostly talk about the type of charging, which is the first two, slow charging today. So at least in the municipality of Amsterdam, they care a lot about where to put these charging stations. For example, if you own a restaurant, you care about like what type of charging stations do you want. Like the University of Eindhoven, where I am, they're going to build a new parking lot. They care about how many charging stations do they need. I mean, I actually asked them for their data. They just gave all their data to me of all the charging stations up to now. They were quite eager to share it and to see if we can find something. I'm not going to talk about this today, but I think it's like this all capacity expansion problems. Also, the ability to charge a battery fast is that something that people worry about. Like you tank your car, you put gasoline in it. Ideally, should be as fast as the traditional gasoline. That will help people transition. However, suppose we are all able to do this. So suppose that we put millions of charging stations everywhere, and our batteries can charge at let's say infinite speed. Like, are we going to be happy? And the answer is no. Then it's just the bottleneck. At least that's the motivation of this talk. The bottleneck is going to shift to the grid itself. So this is I don't know if somebody from Lochem is watching the live stream. But so I will not say anything funny about it. But it's like a remote. It's a remote part of the Netherlands. Let's say the New Mexico of the Netherlands, where we experiment with our energy, and it's actually a very nice region there. And so they actually they looked at a scenario, 2025, where people come home from work hungry with an empty battery. So they want to charge their car and bake a pizza. So the distribution company offered a free champagne breakfast if they were able to burn something. And so they tried. And the experiment started at 7 o'clock. So I don't know if this works. I don't know if this works, but like actually the first hop at around 7:02, you see a drop in voltage at the bottom. That's 1 Tesla connecting. Like 1 Tesla connecting, your voltage drop 5 volt. So it's kind of pretty significant. So like they charge more and more cars, and then at some point they start baking pizzas, and so around a little bit after 8, they add 1 more Tesla to the network, and then they broke something. So that is somewhere between 2005. This is like, I was not involved in this experience. Those are colleagues from the University of Twente. So they broke something. So they caused something that could not have been prevented with existing control mechanisms. And this is based on a 2025 scenario. So yeah, we need to think about, I mean, the topic of this workshop is real-time decision making. We need to think about how to manage this. Right? There's going to be problems, even in the Dutch grid, which I think is quite good compared to some other countries. Okay. So, all right. So that's kind of like some broad motivational talk. So I'm going to talk about so the way I see it as an applied probabilist, that EV charging is a very nice playground of stochastic processes on interacting networks. So you have the electricity network, obviously. You have also a road network, and then we need to manage that with a communication network on top. It's kind of like everything is here. So of course we have to model. So we're going to look at I-charging stations, so you can think of it as a queuing network where every node is a parking lot. And there are Ki parking spaces. Cars arrive according to Poisson process of rate lambda I. They have some characteristics. Each car has some characteristics which we model with a bivariate probability distribution B and D. So charging requirement B, parking time D. You can imagine that if you arrive, you fill out this information on the charging station. So I'm going to assume that this is known. I'm going to also assume that cars that cannot that find a full parking lot are lost, which is kind of, you could also extend the model. Some of the results, at least heuristically, can be extended, that people try to park somewhere else. If I see what happens on the TUE campus, there are only a very limited number of parking lots for electric cars, and then if they're all full, you always have the option to park on a position where there is no charging station. But so in this model, we assume that the cars that find a full lot, so Ki parking spaces in this context means Ki parking spaces where there is the possibility to charge your vehicle. Okay, so bivariate distribution for charging requirements and parking time. So then I'm going to keep track on the number of electric vehicles at every parking lot, and then also the number of vehicles that are not yet charged. And what we are interested in is how to charge those cars while keeping voltage drop bounded. Yes?
Charging requirement is measured in time or in
It's, excuse me?
B's measured is the units for B is time?
No. It's how much you want your battery to be charged.
Energy.
Yes. Any other questions? Yeah.
On your parking lot, so that you plug it on as soon as you get there, or do you go into some sort of queue typically?
No. So that's an excellent question. So there are, for example, if I go back to this picture, this, for example, what you refer, like, there are different ways of like this fast charging. At Fastnet, you would have like a very limited number of cars charging their cars at a fast rate. Other cars will wait in a queue. I'm not looking at that. I'm more looking at a case where there are where this is not happening. So where the charging will be a little bit slower, but I'll go in more detail later. So actually, when I'm teaching queuing, I teach the Erlang loss model. So first of all, for those of you who know a little bit of queuing, if I look at the case where we don't have to charge the cars and there is just one parking lot, it's an Erlang loss model. Okay. Also, like if there's just one parking lot, if there is one parking lot of infinite size and the parking times are infinitely long, or they're just customers leave after they are charged, it's going to be processor sharing queue. This is how I'm going to model the single node, single class, but I'm going to look at the multi-class extension of that. It's just a side remark. I'll come back to that later. So there's actually not that much work. Like probably I missed it, but like Larsen has a paper on where he's looking at parking lots, and he's using Erlang loss models, but there's not that much work. Jelena Judinova has worked on something that's more fast charging. She looks at some kind of ideas that are reminiscent of what other people like Srikant and also Stoljar have worked on, and others closer to the typical stochastic networks, like the max weight type of algorithms, or applied to fast charging, but not really taking into account voltage drops. One motivation for this study is paper where Frank, also one of the organizers of this workshop, is involved in, is a paper where they actually look at the model that we are looking at, and they don't have upper bound on parking lots. They don't have impatience. They don't have the model that people are leaving because they simply are done shopping or something, and then they simulate this system. So they run simulations, but no math. And in that model, so James Cruz and Seva Sneer from Edinburgh are looking at the stability condition of their model under Markovian assumption. And so it's almost finished, and I think it's going to be nice work. Bug them, because otherwise they might not finish it. All right. Hi, James. So, all right. So what I'm going to do is I'm going to, like, one of the things I'm going to do, at least for the purpose of this talk, I'm going to look at tractable load flow model. So first of all, like I showed you these graphs of this experiment where we're keeping all the three phases. We're not going to do that, so I'm not going to model frequency. I'm going to look at like a quasi-steady state process where I'm just focusing on voltage. And like this, so we're talking about electric vehicles, so you're in the distribution grid, which is a tree network. And in the tree network, like the AC power flow equations are pretty tractable, but at least for this talk, I'm going to make a further simplification, and I'm going to model the voltages in the network with a linearized disk flow, which I learned when I was visiting Caltech. So so essentially, if you look at a line network, the linearized disk flow approximation, the voltage drop, like if you park your car twice as far, like you have two options. You park it in the middle of the network or at the end, then that would lead to a voltage drop that would be twice as big. So that's how you can think about this approximation. So you typically sum up over all the vehicles that take power. I'm not actually in this model considering the fact that other people are using. We can talk about this later. So I'm just focusing on the electric vehicles alone in the system. Okay. I'll later go to the special case of a line topology where these formulas are going to be a little bit simpler. All right. So some of our results, I'll comment on that, like hold also for more general AC. So I'm only considering active power here. Like, it is reasonable in the sense that the batteries of the cars only need active power, but the equations, like, it would be more interesting as an extension to also consider the fact that you can support the voltage drop with the reactive power support, but it's not at the moment in the model. Okay, so the question now is, suppose we have a static situation, how are we going to charge the car? We have seen, Vivek, do you have a question?
What are the units of all these things? What are the units of W and these R resistance?
They are like, yeah, I normalized everything. So it's a good question, but I kind of normalized everything. So I assume that at the feeder, for example, you have 240 volts at the feeder of the network, and we want to stay within 10% of that bound. So everything is going to be relative to what is at the node of the network where we have the connection with the higher voltage grid.
So I only have to worry about the Z's, really?
Yeah. So the Z's are going to be dynamic, and then the P's also, they're going to be a function of Z. I'm going to explain that now. And then you have like this function that gives you the voltages. All right. So this is something that people in the stochastic network community are more familiar with, but others probably not. So I'm going to look at this. So suppose we have a static situation, and we have a vector describing the number of uncharged vehicles in the network, and we need to charge them. And we need to decide how much power to allocate to all of these vehicles. So what we're going to do is we're gonna say that if we're going to charge power to one particular vehicle in one particular point in time, we assign this a utility, for example, this weighted logarithmic utility, and then we're going to maximize the sum of all the utilities subject to the fact that we can only charge batteries at a certain rate, and we're not allowed to burn any fuses, and we want to keep the voltage drop. Within limits, acceptable limits. And this is the type of allocation mechanism. So there's a lot of things to be said here in the sense that it's kind of a myopic strategy. It looks a little bit like what OPF is doing. However, here you would like to assign your utility based on how much time you stay in a system to be parked and how much additional power you need to fill your battery with. So it's kind of, but you can fix this by extending this model to a multi-class model where you jump from one class to another based on where you are with your profile. And that so for the purpose of this talk, I keep it a single class. So this is the static situation. So this is when you look at the linearized disk flow, this is a pretty nice optimization problem if a UI is assumed to be strictly concave. In general, for general AC, this is still pretty nice in the sense that its convex relaxation gives you the exact solution because it's a tree network. Stephen Lowe, in one of his surveys, it falls under that framework. So that works. So, of course, like these utility functions, where you get them from. So Frank did a lot of work in communication networks, and here it should be a little bit easier because like we have this OPF style of problems already. But you can imagine that cars will have their batteries will be operated by software, and they're going to decide based on prices how fast they're going to charge. So there's still a lot of room for improvement here in the formulation. But so we're just going to take this as given and then see how we're doing in this talk.
Bert?
Yes.
So the P is in power, but the EV energy demand is in energy, or?
Yeah, here like I'm an imposter. Actually, I'm not really an electrical engineer, but yeah, you need to be careful in defining these things properly. Yeah.
But you can think of this as so every minute you solve this and you get the P.
So that's another excellent question. So I assume that I am solving this yeah, that will give a lot of communication overhead. And I think if you want to implement this, you should solve it every minute. And then the constraints, the voltage constraint should be a chance constraint, probably. But that will make it harder. But right now, I assume that somebody is solving this for me at every instant in time. I'm going to look at a continuous time model. So, but yeah, in practice, you want to solve this as discrete instance, and then there's going to be a trade-off in the reliability versus communication overhead. And I'm not considering that right now. Yes.
Because of energy, then there will be a constraint temporarily in terms of energy. If there's energy.
Yeah, there will. This is a very simple version. Other questions?
So, could you explain what is the physical meaning of the utility function for the EVs?
The physical meaning of what? It's the instant reward I assign as a consumer for being served at this rate. So.
Does not have, say, direct relation with how long you will be waiting.
No, that would like if you want to model that, you need a multi-class extension. For example, you see how much time do I stay parked in the system versus how much more energy do I need. You look at that ratio. Based on that, you make a decision. You could do that, but then it would be a more complicated notation. But in particular, I mean, in principle, if we chunk it up into finitely many segments of this ratio, our model would be able to handle it. But I'm just giving a single class version here. Yeah.
Where are the pizzas here?
Excuse me?
Where are the pizzas? The constraints, the grid constraints depend not just on the EV charging, but on the other.
Yeah, that's true. So they're not here. No, they should be included. If you want to move closer to practice, you need to include the pizzas, the buildings, everything. Yeah, they're not here. True. So that also makes it simpler in the sense that these constraints. Yeah, you probably the model should be way more complicated. Yeah. Okay. Other questions? All right. So. The model should be more complicated, but instead, let's make it, at least for a second, a little bit simpler. So the question is, like, is there like I'm in a queuing background. So are there like instances where you can find an explicit solution of this model? And the answer is yes. So if the only constraint is the voltage drop, so the top two constraints here are not active, and there are like infinitely many parking lots, and you take the logarithmic, unweighted logarithmic utility function, then the system essentially reduces to a multi-class processor sharing queue. So that is like but that seems to be in the case of a line network. That seems to be the only case where you can imagine now. So the connection with so processor sharing, as I said, is a service discipline where we serve all customers at the same rate. And the idea here is that if I park at node I, my effective service time is the amount of energy I need multiplied with the sum of the resistances across the line from that node to the feeder. I need to multiply it with that. And then you can see it as a multi-class processor sharing queue. And provided that some stability condition holds. And okay, but that's about it. So processor sharing was suggested in the past for several other applications like communication networks, and also the original application was a mainframe computer systems. Okay, but in general, it's not that easy. So the model is very simple, but if you keep in mind that there is also stochastic dynamics going on. So what you get is like at every given moment of time, you have a measure valued processor where like for every node we're keeping track of the cars as particles, and they're interacting because of the scheduling discipline. They're interacting, and all these particles move to the southwest at a certain rate, depending on because their parking time is expiring at a constant rate, but there is interaction in how you charge the car. So it's very complicated. Especially if you don't want to assume exponential service times. And even if you do want to assume exponential service times, then the Markov chain is pretty ugly. So actually this is a typo. So you need to solve of the order of k to the power 2r convex optimization problems just to fill the rate matrix, the Q matrix. So for every element, you need to solve an optimization problem. What I usually do in this case is I send an email to Arkady Nemirovsky asking what should I do. And he asked, he basically, I mean, we are going to show you some examples for the case of 2 nodes and k is equal to 50. He recommended just to solve them one by one. But like the optimization problems are very similar in the sense that you slightly change the criterion function. You put a little zi and a little zi, and it's like, he basically says like if it's of the order of billions, then don't bother. But if it's going to be like 10 to the power 12 or more, you should do something else. But like, even then, it's like if you have no exponential distributions, then that's just hopeless. So we do something else, and that's we're gonna approximate things with a fluid. So this is, I did not make this picture myself. There was like at some point some artist, I wrote some popular scientific article about fluid approximations, and then there was somebody drew this. So the idea is we're gonna approximate these particles with a fluid, and so you can do this in multiple ways. You can do this formally. So formally, I mean, with formally, I'm a mathematician. I mean, really formally, not formally as if you don't make it rigorous, but like, okay, you can consider it any way you want. But if you want to do this, you need to look at the scaled system of models indexed by n. You can scale up the capacity, you can scale up the arrival rate, you can scale up the number of parking rates, and then if you do that, you can expect in the limit some deterministic dynamical system to appear, and then you would like to study its invariant point. So I'm not going to go into how to make this all rigorous, and I'll just give you a result on how the invariant point of this system would look. So it turns out that if you do this type of scaling, you can characterize, so we have looked at this OPF type of problem, and on top of that you have then the stochastic dynamics, but it turns out that if you do this type of fluid scaling, then at least the invariant point has a complexity which is very similar to the original scheduling discipline in the static case. So that's good. And so the result is that this invariant point Z star can be expressed in terms of the solution of an optimization problem, which is, as I said, very similar to the OPF type of problem before, just with a different criterion function. And a criterion function has some information about the joint distribution of the charging and the parking times, as well as the utility function. And so everything is there. The network constraints, the network is in the constraint. So you have like the stochastic dynamics, the utility function, and the physical network constraints. They're all in this optimization program. And GI is concave, so this is good. You can solve this. It's just not 10 to the power 12 OPFs, but just 1. That's good. And so how do you do this? So you can actually, from that, compute the fraction of cars that get successfully charged if you know the joint distribution. So how to do this? So that's the idea. It's like in queuing, we always used to say in queuing theory, little is known, but little is known. So we are going to apply, for the purpose of this talk, we're going to apply Little's law heuristically. So Little's law says that the expected number of customers in the system is the arrival rate times the time you spent in the system. So arrival rate here is just the arrival rate in an Erlang loss system. So we know that's this gamma I. And then how much time do I spend in the system? Well, how much time I spend in the system is the minimum of my parking time and the time I am considered to be an uncharged vehicle. Now the time I am considered to be an uncharged vehicle is the amount of energy I need divided by the rate I get the energy. Steve, thank you for correcting my terminology again. So, what is the rate? Well, in steady state, we're thinking of a big system. Everything is balanced. So you can heuristically apply the snapshot principle that you stay in a system for a very relatively short time. So your rate is going to be this pi of Z star. So if you then plug this in, you get an equation, and you want to solve this equation And usually you try to do some contraction mapping argument, but that doesn't work here. But what you can do is, and this is a trick that I learned from all the work of Frank Kelly on loss networks, but I mean it has appeared in other settings as well. So you add this approximate version of Little's law to the KKT conditions for the optimization problem that defines P of Z. You massage the whole thing, and then it turns out that this new set of equations, so the old KKT condition, and then for Z star, and then his equation for Z star, you can then from that whole set of equations recognize that that is actually the set of KKT conditions of this problem. You have to guess it, but I mean, if you've seen it once, you know how to do it. So, okay, that's kind of the way you show this. That actually still works for AC, and then you have to be a little bit more careful. But the fact that the convex relaxation is exact helps in this case. So this whole thing would still work for a more general load flow model. Okay. So, yes.
The problem in the previous slide is that still complex?
Excuse me. Yeah, because I look at the linearized disk flow. So the capacity, the set over which I optimize here is actually polyhedral. And G, the function G is also, you can use some probability theory to show that G, because it's a composition of a concave function with the inverse of this expected value function, and yeah, you can show that it's concave. Yeah. So we did some little validation. So we compare, first of all, I mean, you can still solve. This is just if you only have a load. The voltage constraint is the only constraint. Just a little network of a line network of 2 parking lots. We computed the expected number of jobs in the system. Everything is exponential, and compared to the disk flow approximation with the AC. And so you see that the disk flow, at least for this purpose, seems to be a reasonable approximation. Then we compared we look also at the fluid approximations, both for disk flow and AC, and we compare them with the expected value. We compare them with each other. You also see that here also the impact of approximating AC with disk flow is not going to harm you that much. Then the question, of course, is how good is the fluid approximation to the stochastic model? That's also pretty good. It gets worse if you add all the capacity constraints, but it's still within 10% relative error. And I mean, for bigger systems, we cannot really compute the whole Markov chain invariant distribution anymore. So then the obvious question then is like, okay, how do we? The next question is that like, how are we going to? Can we use this to set the weights in a utility function? So consider now a setting where you these utility functions are logarithmic with weights, and then the question is how to set those weights. So the first thing you may wonder is how to set the weights in a way that everybody gets charged at the same rate, and then that really depends on how far you are from the connection to the high voltage grid. Like the further away you are, the bigger weight you should get. Otherwise you're not getting charged a lot. So, but that's not very efficient. So another type of question you can wonder is like, how can we set the weights in such a way to maximize the throughput? And again, weighted proportional fairness, then the weight should be different. You can play a little bit with this optimization problem, and then you get this type of resource allocation problem. So the fraction of cars that is charged successfully at parking lot I, or like not the fraction, but the total number of cars, the rate of cars that is charged successfully at node I is then this gamma I times this probability. And the weights appear there, and it's subject to a constraint, which the voltage drop, which looks then like this. And you can then, depending on the joint distribution of B and D, try to solve this. And so I'll give you 2 examples on how the solution looks. So the first kind of thing we looked at is that B is equal to a deterministic constant times D. So everybody expects to get charged at a certain rate. This is proportional to the amount of time they are parking. if you look at that, so it's actually an interesting example because this is actually the distribution that achieves the distributionally robust solution to this problem. If I want to do distributionally robust optimization subject to the fact that that B and D have given means, and I solve this problem, then it turns out that this is distributionally robust solution. So that gives you a knapsack style problem. And you see from this problem is that this knapsack style problem is that people who are going to park down the street will get in trouble if there is a overload in the network, which is something you need to be aware of at least. I mean, it's a very simple model, of course, no reactive power support and so on, but still. If you look at the case of a decreasing failure rate, then this resource allocation problem is nice and convex and you can solve it. And then if you do this numerically, you get solutions like this. So you really see, if we look at a load of 120% and we need to decide what to do, and we have this performance criterion, and we want to maximize the fraction of people that meet their target, then the cars that will be parked at the end of the street are going to get nothing. And in this Pareto case, it is more diffuse. So, of course, this criterion of like, I now put a 0-1 reward function. You could also argue that if I get charged enough so I can make it home, I'm also happy. On the other hand, maybe that's what we started with, that we already started the bare minimum. So, I mean, this is just like a more preliminary experiment, but it's kind of, I found it at least interesting. So now just a little bit more on the math. So it's also related to an earlier question of Stephen. So if you look at this, the fluid model dynamically, then you get like, I mean, it's not really. You can try to model this as you can write down a partial differential equation if you want, but you can also write it like this. Then it's not a differential equation anymore. It's a functional equation. And you can prove here, there's this useful book, also a nice book of Bonans and Shapiro. You open up to page 261, I think, and then you apply that theorem. And you can prove that P of Z is Lipschitz continuous in Z. And you can also show that P of Z is non-increasing, and those two properties together allows you to prove that this set of equations has a unique solution. And so then the question is, how do you show that there is a unique invariant point? I mean, you can, if you're good in finding Lyapunov functions, go ahead. I'm not so, you can exploit the monotonicity of the system here. So there's a very nice trick that in a different setting a former PhD student of mine, Masha Frokova, found, and it's also applicable here. So you define a lim inf and a lim sub. You use some other information to show that they are strictly positive and strictly finite, and then you use these fluid equations to get a set of equations for the lim inf and the lim sub, which are given here, and then from the monotonicity of PZ and this characterization of Z star in terms of this OPF problem with the G criterion function, using the Little's law, you can prove that this whole set of systems has a unique solution, and that gives you the convergence. Okay, so there are like lots of, so there's like a preprint on the archive, and that also contains the multi-class extension. I mean, we're currently working on a rigorous justification of the fluid scaling where we also try to do the AC. There are lots of things that are not in here. So the time-dependent behavior is, I think, like steady state here is probably not the most interesting thing from a practical standpoint. I think the utility framework can be further refined. Discretizing time might be an interesting problem as well. And of course, like having the buildings and the fridges and the pizzas in the model, that would be also nice. But for now, this is it. Thank you for your attention. Yeah.
Why do you have the log function in your utility? Is it?
Because it works well mathematically. I mean, there are actually better arguments. It has all kinds of nice properties. And so in the setting of communication networks, Frank Kelly, you can also read that in his textbook with UDNova, shows that even if you don't know the utility function, if you use this weighted logarithmic utility function and you set the weights carefully, you can achieve system-wide optimum in a distributed fashion. So there are also good reasons. And it also happens to work mathematically very nice. Yeah.
So you have this very nice structure, spatial structure, where you have multiple charging stations. That's spatial, and then you consider the power constraints on that network. Is it possible to extend it to include transportation dynamics as well, since you already have the spatial structure?
Yeah, so up to some extent. So the first thing that we assume is indeed that the cars arrive at some rate lambda I, and then if they find a full parking rate, they're lost. Then the question, of course, in practice, they're not lost, they're going to repark. So we actually got 2 years of charging data from the TUE campus, and we don't know who physically parked there, but we have their tags. So we can say, okay, car number 1345 tried to park here on Monday, but then on Tuesday arrived 10 minutes later and then went parking there. We're trying to now figure that out, how people behave from data. I don't know how far we'll get, but yeah, that would be nice, like to get some feeling on how people behave and then include this in the model. But you could also argue that, for example, if you want to look at the university campus, I mean, you have like you enter with your tag, and then people know you enter, and then you get an app saying like there is still a position available there, that you have some joint routing of. I guess that the parking of the car is like it's especially the beginning and the end of the day, but that you have some, that you integrate this in a way that would be nice.
I'm actually more thinking of the cars have to transport between points A's and B's and C's and use up their energy.
The transport of what? Of the cars?
Let's say you have a taxi fleet, for example.
A taxi fleet, yeah.
Right. So the taxis will fetch people around and move around the transportation network.
Yes.
They will consume energy, and then they will say, okay, I need to charge.
Mm-hmm.
Right. So there's a transportation dynamics as well.
Yes.
You interact with the chargings and power flows.
That's true. Yeah. So I guess like the model here, I would say that you could say, for example, okay, somebody needs to get charged, and then you would like to know that which are the nearest two locations where there is space available to charge, we're thinking in the context of battery swapping about a model where we have some power of two type of choice where you then can go, like there are like a bunch of locations close to you, and you take the one where there is the most capacity. Yeah.
Thank you very much. There's snacks and coffee outside for the break. We'll resume at 10:45. A few advanced administrative